Something is terribly wrong with the atmosphere right now, and I don't mean that loosely. I mean that on a single calendar day, April 11th, the United States was simultaneously being hammered by severe thunderstorms on the southern high plains, a tornado watch covering chunks of Nebraska, active wildfire conditions in Colorado, flooding rivers in Wisconsin and the Mississippi Delta region, a geomagnetic disturbance rattling Earth's magnetic field from space, and the ground itself shaking off the coast of California and out in the Bering Sea near Alaska. One day. All of that. One single day. And the kicker? Most people had absolutely no idea any of it was happening. That's exactly why you're here. And that's exactly why I'm going to walk you through every single piece of this. Because taken individually, each of these events is significant. But when you step back and look at the full picture, and I mean the full picture, what was unfolding on April 11th was something genuinely extraordinary. Stay with me, because by the time we get to the end of this, you are going to look at that date very differently. If this kind of deep dive atmospheric chaos coverage is what you're into, do yourself a favour and subscribe right now, because this channel exists for exactly this reason. And drop a comment below. Tell me which part of this surprised you the most. I genuinely want to know what's landing for you. Now, let's get into it. Let's start in the place where the atmosphere was most visibly losing its mind. West Texas, eastern New Mexico, the Texas Panhandle. Yesterday afternoon, while a lot of people in those areas were going about their normal Friday, the sky was doing something that meteorologists recognize immediately and respect deeply. Supercells were firing along the dry line. Now, if you're not familiar with the dry line, let me explain it in a way that actually makes sense. Imagine you're standing on a street and on your left side the air is bone dry, desert dry, the kind of dry that feels like the inside of a hairdryer, and on your right side the air is thick, muggy, loaded with Gulf moisture that has been streaming northward for days. The line between those two air masses is the dry line, and when those two air masses collide in the afternoon heating hours of a spring day in the southern plains, you don't just get thunderstorms, you get supercells. Organised, rotating, intense supercells, the meteorological equivalent of loading a machine and pointing it directly at the surface. And that's exactly what happened. Storms tracked eastward, bringing hail up to 2.5 inches in diameter. Let that land for a second. 2.5 inches. That is not pea-sized hail. That is not quarter-sized hail. That is a baseball approaching the surface at terminal velocity. We are talking about hail that dents hoods, shatters windshields, strips bark off trees, and sends animals running for cover. And it wasn't just the hail. Wind gusts were recorded up to 70 miles per hour. 70. That is a borderline Category 1 hurricane wind speed. Not from a tropical system, not from a coastline. From a supercell thunderstorm rolling across the southern high plains on a Thursday afternoon in April. There was also a low-end tornado threat accompanying these storms, with isolated 2% tornado probabilities in play. And while 2% might sound small to you, here's why that number matters. That 2% applies to any given point within a large defined area. In aggregate, across the entire storm-affected region, the real risk picture is considerably more serious than a single number suggests. The Storm Prediction Center had this area under a slight risk, a 2 out of 5 on the scale. But here's something I want you to understand about slight risk days. The word slight is criminally misleading. Significant severe weather, including tornadoes, large hail, and damaging winds, happens on slight risk days all the time. The word slight is a probabilistic forecast term, not a description of severity. On a slight risk day, you can still have an extreme tornado. You can still have a hail-producing supercell that totals your car. The risk to any individual in that zone is still very real, and this setup, dryline firing, surface instability building through the afternoon, storms tracking eastward, this is textbook spring plains severe weather. This is what April was made for in Texas, and it was only the beginning of what was unfolding across the central United States, because we haven't even talked about Nebraska yet. And that's where things get even more interesting. Here's the part that matters most about the Nebraska situation. The Storm Prediction Center didn't just flag severe weather for Nebraska on April 11th. The National Weather Service out of Lincoln issued an actual tornado watch. A watch. Not a warning. A watch. That means conditions were favourable enough for tornado development that forecasters needed to put an entire region on notice hours in advance. The watch was valid until 11 p.m. Central Daylight Time, covering portions of central, southern, and eastern Nebraska. And think about that timing for a second. 11 p.m. Central Time. That means this was a nighttime severe weather threat, and here's why this should concern you more than the daytime storms in Texas. When supercells and severe storms fire at night, the visual cues that people rely on, the greenish sky, the ominous rotating wall cloud you can see from a mile away, those go dark, literally. You cannot see a tornado coming at night the way you can in daylight. Your warning time compresses. Your ability to make the call to shelter is reduced. Nighttime tornadoes are disproportionately high impact for exactly this reason. So the fact that this watch extended deep into the evening hours in Nebraska is not a minor footnote. It is a critical detail. The dynamics driving the Nebraska severe weather were different from the dry line setup in Texas, and that's actually more alarming than it sounds, because it means the atmospheric forcing was coming from multiple directions simultaneously. In Nebraska, it was warm front lift and upper-level jet dynamics doing the heavy lifting. Picture a warm front as a ramp. It forces warm, moist surface air upward along its boundary, and when you combine that upward lift with a screaming upper-level jet stream overhead providing wind shear, the change in wind speed and direction with height that allows thunderstorm updrafts to rotate, you get exactly the kind of environment that produces supercells with rotating updrafts. Ping-pong ball-sized hail was possible, wind gusts up to 65 miles per hour were in play, and the tornado risk, while low-end, was real and organised enough that the NWS put a watch out. Two separate severe weather setups, two different meteorological mechanisms, same day, same country, running simultaneously hundreds of miles apart. That is not a coincidence. That is the signature of a large-scale, multi-day severe weather pattern dominating the central United States. And when you see multi-day reload cycles like this, where the atmosphere just keeps spinning up new setups day after day, that's when the cumulative impact starts to compound. Which brings me to the flooding, because the ground in this country was already soaking. Let me take you to Wisconsin. The Wolf River at Shiocton was sitting at 13 feet on April 11th, above flood stage, not approaching flood stage, above it by several feet. And this is where I need to explain something called hydrological lag, because it is one of the most underappreciated and genuinely high-risk concepts in severe weather. When it rains heavily over a drainage basin, the water doesn't just instantly appear in the river. It takes time, it soaks into the soil, it runs off into streams, those streams feed into tributaries, those tributaries eventually reach the main river channel, and that whole process can take hours, days, or even longer, depending on how saturated the ground already is. And here is the critical piece. If the ground is already soaked from previous rainfall events, which it absolutely was in Wisconsin, after a wet early April, then the lag time shrinks dramatically, and the peak river levels go significantly higher than they would under normal conditions. The soil has no more room, the rain has nowhere to go but into the river, and once the river is above flood stage and additional rain chances are still in the forecast, you're not dealing with a one-time event. You're dealing with a prolonged, sustained flooding situation that doesn't just fix itself overnight. New London was sitting at 10 feet. Levels were slowly receding, but this was a slow, grinding, ugly flood situation. The kind that doesn't make the dramatic headlines of a flash flood, but quietly inundates basements and agricultural land for days at a time. And Wisconsin wasn't alone. The St. Francis River, further south, was also running at elevated stages on April 11th, approaching the moderate flood category, near the 27-foot threshold in spots. This is from heavy rainfall events earlier in April that had never fully drained out of the system. Same story, different river, antecedent moisture. That's the technical term for the moisture already present in the soil and river systems before a new rainfall event, was running well above normal across a broad swathe of the central and eastern United States. And what does that mean for the next round of storms? It means the ground cannot absorb what falls. It means flash flooding potential is elevated even in areas that haven't seen recent rain. It means the atmosphere had already stacked the deck before a single new storm developed. Keep that in mind as the storm pattern continued to evolve, because this is all connected. Now I want to take you west, to Colorado, because while the Central Plains were dealing with severe thunderstorms and Nebraska was under a tornado watch, the Southwest was dealing with a completely opposite but equally high-risk atmospheric extreme: dry, gusty, critical. Mesa County issued a no-burn advisory through the weekend on April 11th. The National Weather Service in Grand Junction flagged elevated wildfire risk across parts of the southwest as dry fuels, gusty winds up to 35 miles per hour, and critically low humidity combined to meet red flag criteria. Red flag. Let me tell you what red flag actually means in plain language. It means that if a fire starts, from a campfire, from a spark off a vehicle, from a downed power line, from anything, the conditions are so favourable for rapid fire spread that crews may not be able to contain it before it becomes a major incident. The wind carries the embers, the dry fuels ignite instantly. The low humidity prevents any natural moisture in the vegetation from acting as a buffer. Red flag conditions are not a warning to be cautious. They are a warning that the margin for error is essentially zero. And to prove how real that risk was, the Energy Lake fire burned 84 acres before crews were able to fully contain it on April 11th. 84 acres. Contained. And while containment is absolutely good news and those fire crews deserve enormous credit, 84 acres of fire burning during a red flag day in April tells you everything you need to know about how dry and volatile those fuel conditions were. The cause is still under investigation, but the conditions were a perfect ignition environment. And here's what I need you to understand about the geographic context of all of this. West Texas and the Texas Panhandle are severe storm country. Nebraska is tornado country. Wisconsin is flood country. Colorado is fire country. And on April 11th, all of those things were happening at the same time, all driven by the same broad-scale atmospheric pattern. A progressive trough, an associated surface cyclone dragging warm, unstable air northward on its east side, while wringing moisture out of the atmosphere in some places and desiccating the air in others. One atmospheric system, multiple simultaneous historic event signatures, that is a genuinely alarming situation, and we haven't even gotten off the planet yet. Because while all of this was happening on the surface, things were also stirring in space. NOAA's Space Weather Prediction Center was tracking active geomagnetic conditions on April 11th, driven by fast solar wind streaming from a coronal hole in the sun. Now here's your space weather explanation in terms that actually make sense. The sun is constantly emitting a stream of charged particles called the solar wind, but not all parts of the sun emit at the same rate. Coronal holes, regions where the sun's magnetic field opens outward instead of looping back on itself, act like high-pressure jets, firing solar wind at much higher speeds than normal. On April 11th, that solar wind was hitting Earth's magnetic field at around 550 kilometers per second. That is not a slow drift. That is a fire hose. When that fast solar wind hits Earth's magnetosphere, it compresses it, it distorts it, and it drives geomagnetic activity that we measure using something called the KP index, a scale from 0 to 9. On April 11th, the KP index reached 4 active levels. Forecasters had actually issued a G1 geomagnetic storm watch, G1 being the lowest level on the 5-point storm scale. But the event ultimately fell short of full storm thresholds. What it didn't fall short of was generating real magnetospheric activity that can affect satellite operations, GPS accuracy, HF radio communications, and potentially power grid stability at high latitudes. And here's a detail that I think deserves more attention than it typically gets. This wasn't a coronal mass ejection, the dramatic headline-grabbing solar eruption that gets all the press. This was a coronal hole stream, a co-rotating interaction region, a recurring, predictable, cycling feature of the sun's structure, and yet it still pushed the KP to 4. Imagine what a direct CME hit during a period of elevated solar activity would look like on top of an already active geomagnetic baseline. Let that sink in. But stay with me, because the Earth itself wasn't done making news. 2 earthquakes on April 11th. Different coasts, different tectonic contexts. Same day. At 11:12 in the morning, a magnitude 3.4 earthquake struck offshore near Trinidad in Humboldt County, California, about 28 kilometers northwest of Trinidad, at a depth of 21 kilometers. Light shaking was reported in coastal communities. No damage, no injuries. But here is what makes this location significant in a way that a simple magnitude number does not capture. This epicenter sits near the boundary of the Cascadia subduction zone, one of the most seismically high-risk fault systems in North America. The Juan de Fuca plate is slowly, relentlessly, diving beneath the North American plate along this boundary, and the strain that builds up in that process has to go somewhere. Most of the time, it releases in small microseismic events exactly like this one. Magnitude 3.4, a tremor, a tiny pressure release on a fault system capable of producing a magnitude 9 megathrust earthquake that would dwarf anything in American recorded history. Every small earthquake on the Cascadia boundary is the fault system speaking. It's telling you the plates are still moving, the stress is still accumulating, and out in the Bering Sea, 187 kilometers east-southeast of Atka, in Alaska's Aleutian Chain, a magnitude 4.7 earthquake rattled the seafloor at a depth of about 54 kilometers. No tsunami warning, no damage. But again, the Aleutian subduction zone is one of the most seismically active environments on Earth. Pacific plate convergence at depth produces these events routinely. But routine does not mean insignificant. It means the system is alive and active and the energy is moving. And then there's one final piece of this puzzle that I think ties the whole atmospheric story together in a way that makes the April 11th picture even more alarming. The southeast was baking. Georgia, the mid-Atlantic, temperatures running 10 to 15 degrees Fahrenheit above seasonal norms. Cobb County, Georgia, hit 85 degrees Fahrenheit on April 11th, in the middle of April. That is not a warm spring day. That is a summer temperature arriving a season early. And here is why that matters far beyond just the discomfort of people in Atlanta reaching for their air conditioners in April. That anomalous warmth in the southeast was not an isolated feature. It was the product of a persistent high-pressure ridge parked over the region, pumping warm air northward from the Gulf of Mexico, and that same Gulf moisture was feeding the severe weather setups in Texas and Nebraska. The warmth in Georgia and the storms in the Central Plains were part of the same circulation. The ridge feeding warmth into the southeast was the flip side of the trough driving the storm systems westward. It's a classic spring pattern. A big atmospheric wave with warmth and ridging on one side and active severe weather on the other. But the amplitude of that wave, the degree of the temperature anomaly on the warm side, tells you something important about how loaded the atmosphere was. 15 degrees above normal in the southeast while supercells are firing in Texas and a tornado watch is active in Nebraska. That contrast, that temperature and moisture gradient between the hot, humid southeast and the volatile storm zone of the Central Plains, that contrast is the fuel. That gradient is the engine. The bigger that contrast, the more atmospheric potential energy is available to be released in the form of thunderstorms, tornadoes, and severe wind events. And on April 11th, that contrast was enormous. This is what I want you to take away from all of this. These events were not separate, unrelated things happening coincidentally on the same calendar day. The Texas supercells, the Nebraska tornado watch, the Wisconsin flooding, the Colorado fire weather, the warm anomaly in Georgia, they were all expressions of the same large-scale atmospheric configuration playing out across the continental United States simultaneously. The rivers were flooding because the ground was saturated from weeks of above-normal precipitation driven by an active storm track. The fires were burning because the storm track had wrung the moisture out of the southwest while pumping it eastward. The severe storms were firing because the same pattern that was starving Colorado of moisture was flooding the plains with Gulf warmth and instability. And up above, the geomagnetic environment was stirring because the sun's own activity cycle was feeding fast solar wind toward a planet already in meteorological turmoil, and beneath it all, the plates were moving. They are always moving. The Cascadia boundary is always accumulating strain. The Aleutian Arc is always cycling through its seismic rhythms. April 11th was not just a severe weather day, it was a full-spectrum, multi-system, multi-hazard event across an entire nation, and most people scrolled right past it. So here is the question I want to leave you with. When you see a day like April 11th, when the atmosphere, the oceans, the land, and even the sun are all simultaneously expressing instability in their own ways, do you think that's a coincidence? Do you think these systems are truly independent of one another? Or do you think there's a larger, more interconnected story about the state of Earth's energy balance and atmospheric dynamics that we're only beginning to understand through events like this one? I'd genuinely love to know what you think. Drop it in the comments below, your reaction, your theory, your question. And if you made it to the end of this video, you're exactly the kind of person this channel was built for. Subscribe if you haven't already, because we do this kind of deep, connected, full-picture atmospheric coverage every single time something like this happens. And given the state of the pattern right now, it's going to happen again very soon.